Alright, so we've been introduced to vectors, right? We've done some things with it. We've done some magnitudes and distances, some directions, things like that. We found midpoints. We've expanded into 3 dimensions and at least looked at it and seen how things kind of match up. What we're ready for now is writing equations for vectors. Now this is going to be really helpful for like application problems, and it's used a lot in like computer programming, things like that as well with matrices. Alright, so that's what we're going to look at right now. So what we're going to say, let me just remind you, when you first learned about linear equations, you learned about this equation, y equals mx plus b. Now the value of that y equals mx plus b is that all we needed was a y-intercept, and then we needed to know where to go from that y-intercept, right? Once you had the y-intercept, you could do the slope, up 1 over 2, up 1 over 2, and you could put the points down and create a line. Right? Now those could be done to the right, it could be done in the opposite direction, right? Down 1, left 2, and then it could have been done in fractional amounts as well. Any point on the line would end up working. So x is kind of how many times we're doing that slope, and m is the actual slope itself. Alright, so then what you learned was this one. You learned y minus y1 equals m times x minus x1, point slope form, right? And we learned that this time really all we need is a point, right? You don't even need the y-intercept, you just need any point on the line, and then you need to know the slope because you need to know where to go from there. Again, it could be a whole slope, it could be fractional, it could be multiple, right? And so this idea is going to be helpful as we try to create a vector, a line using vectors. Okay, so what we're going to do is we need to have a starting point, right? Both of these required a starting point. So starting point. We've talked about the vectors that start at O, but OA is what is called the position vector for point A, right? So that would be kind of like this right here up here. That would be the position vector to tell us, okay, this is where we're starting now. Okay, so that's one position on our line. Now from there, what we need to know is the direction, right? We need to know which direction are we going, and so that would then tell us how to go this way, how to go that way. Now the way that this is written kind of in a general format is we write that R is representing the points on the line, is equal to A, which is our starting point, the position vector for A, plus lambda u. Alright, now lambda is what's called a parameter, right, which is kind of like the x up here, showing that something happens over and over and over again, and u is our direction vector. Okay. So as lambda changes, we accomplish that direction vector 1 time, 2 times, half a time, and that takes us to the other points, and it can go negative as well, which means it will cover all the points on our line. So this essentially gives us a starting point and the direction so that we can then create a line using just vectors. Okay? So what I want to do now is just kind of show you an example of that. Okay? So what we're going to do is we're going to consider 2 points. We've got A, which is 1, 3. Now note that I'm doing this in 2 dimensions just so that it's straightforward the first time and so that it's a little bit quicker. You don't need to sit and watch me do this through 3 dimensions. Okay, so let's say that we want to write a vector, an equation for the line containing A and B. Alright, so I need a starting point, alright, and so we're going to use this, alright, so the points on the line will be represented by x and y, okay, and that will be equal to a starting point, and it doesn't matter which one you use, okay, in some situations it might. If this is a real life situation and we know that at time 0 it's at a specific place, that's probably the one you want to put here, okay, and then we're going to go plus lambda times our direction. So we're going to need a direction. So to get the direction, we need to find out what's going from A to B. So we're going to find vector AB, and remember to do that, we just take B minus a, so we go 5 minus 3, which is 2, that's the y value, and the x value would be 2 minus 1. So there's my direction vector. Now it actually doesn't matter in this situation whether it's 1, 2 or it's negative 1, negative 2, right? Because both of those would essentially be the same thing. Going from a to b and b to a would both be on the same line. The difference is in some situations we have an actual object like a boat or you know, a missile or something like that that's going in a specific direction, and so it really does matter, is it going from A to B or is it going from B to A? But here we've actually written an equation for that line. Now what I want to do with this is now actually break it up and show you a couple of other things. Okay, so this is just our vector equation. Alright, what I want to do now is show you how to rewrite this as a parametric equation. Okay, and you will find many times that the parametric equations are very helpful. Okay, what we do is we just take the x parameter, we take the x pieces and break it up. And so we rewrite it as just the top piece right there. X is equal to 1 plus lambda 1, lambda times 1, or essentially just lambda. Now, this you can see would be helpful. All it is like when in physics you deal with just the x components, right? That's essentially what you're doing here. You're just looking at the x components and finding out where does it end up horizontally. Okay, we do the same thing for y. We say y equals 3 plus 2 lambda. Okay, so again, lambda is just how many times I'm going through this. A lot of times lambda can resemble something like time. 1 second I go through one iteration of this, 2 seconds I go through two iterations, and so on and so forth. And so there I got my parametric equations. Now the last thing I want to do is show you now how to get the Cartesian equation. Now the Cartesian equations are actually what you're more used to. That's your y equals mx plus b. That's these things up here, because those are graphed on a normal Cartesian plane using normal Cartesian points. And so that's where we're going to get a point x comma y. And so what we need to do for Cartesian is the lambda's got to go away. The lambda is this parameter thing that is helpful. It's kind of like time, something that links the two equations together, x and y, but yet allows us to work with them separately. But sometimes we just don't want to have to worry about that. We just want to know how our x and y are related. And so to do that, what we're going to do is we're going to solve for lambda. And so here I'm going to subtract the 1. So I'll have lambda equals x minus 1. And here I'm going to subtract the 3. So I'll have lambda equals y minus 3. And of course it'll be divided by 2 there. And so then I've got both of them in lambda. So then what I'll do is I'll put them together because they're both equal to lambda. And so I'll go x minus 1 equals y minus 3 over 2. And then I can solve for y. So I can multiply both sides by that. I'll have 2x minus 2 equals y, still a minus, minus 3. Add the 3 to both sides. I've got 2x plus 1 equals y. And so now I have it in slope-intercept form. I've got my y-intercept and I've got my slope there. Now if you did this using just the variables, you could very easily write this out as something like xy equals a1 or ax, a2. I think in the Oxford book they generally use 1 and 2, though it would make more sense in my brain to use x and y here. And then plus lambda times, and then again they would use u1, u2, just like that. And so you could do what we did here, and you could actually rearrange, and you could find out how to get the y-intercept of any equation given a vector equation. In fact, if you have time right now, go ahead and try that out. See if you can solve here for y in terms of x and find out what the slope is in terms of these things. Find out what the y-intercept is in terms of those things. And just kind of get used to moving the variables around and using the parameters and things like that. In class, we'll go ahead and do some more interesting things with these. All right, I do want to do one last thing with you, and I want to ask you, we want to write the vector equation for a line that is parallel to AB, right, to your first line there, but it goes through a new point, C, which is negative 2 comma 4. All right, so the way that we're going to do this is we're going to, in order for it to be parallel, it has to have the same direction. So we're just going to go x, y equals, and so we've got our starting point, which this time is going to be negative 2, 4, and then plus lambda times, and we'll use the same direction as before, 1, sorry, not over, just 1, 2, because that would put us in the same direction. That's kind of your slope, right? And so that direction will be the same for both lines, and that makes it parallel. Okay, now if you wanted to, you could prove that these are parallel and not collinear just by simply showing that either this line doesn't include that point or this point doesn't include those lines, right? All you would have to do is say, okay, well, let's just plug in negative 2, 4 for x, y, and then solve for lambda. And that may be easier to do here in the parametric equations, right? So maybe I'll deal, and let me just show you that. So we'll take negative 2 and put it in for x. We're going to see if point C is on this line. If it is, then they're actually not parallel, they're actually collinear. Right, so what we'll do is we'll go ahead and put negative 2 in. So we'll say negative 2 is equal to 1 plus lambda, which means here lambda equals negative 3 when I subtract the 1 of the other side. So that was with x, and now we're going to try y. So y should be 4. So 4 equals 3 plus 2 times lambda. We subtract the 3, we get 1 equals 2 lambda. So therefore I've got 1/2 equals lambda. And you'll note that here lambda is different things for both of those. If that's the case, that means that it's at negative 2 at one specific value for this parameter, and it's at 4 for a different value, which means that it's not there at the same time, essentially, which means that this point can't be on that line. These values are on that line, but they're on that line at different places. Okay, so if it would have given you the same parameter, then you would know that it's on the line. And we'll do that a lot. We'll actually have points, and we'll be able to solve for the parameter and be able to use that to help us to create equations and things like that, solve for specific problems. Okay, so that's all I've got for you here, and I think you're probably ready to do some really good vector stuff.